Hi, I'm Rafael Romero, and I am part of Certus's GPIO packages software test team. We are a team that is tasked with creating a test bench for Certus semiconductor that will be used to characterize their custom ASIC's propagation delay, rise, and fall times. Certus Semiconductor, our mentor, is a company that currently specializes in the design of general purpose input outputs, open drain outputs, and low voltage differential signaling device libraries. Currently, Certus relies on third party services to test their custom ASICs, but has given us great tutelage, advice, and industry experience to help us realize an automated test bench. The main scope of our project is to build an automated test bench with devices that hold IVI instrument software architecture library backends. VISA for short, I know it's a mouthful, but VISA is essentially a trusted measurement industry standard for devices. Think equipment like oscilloscopes, waveform generators, equipment that you typically see in the lab. Developers from Python have created a free module called Visa that allows us to control equipment that have VISA backends with standard commands for programmable instruments. This package was leveraged to create our automated test bench. My team members will go through the test bench here shortly. It is also noted that this was a combined effort with the hardware team who designed the PCB, which will hold Certus's ASIC as well as ports for our test bench.
Hi, my name is Kyle. I'm going to be running you through the hardware section of our project. So this is the layout. So here's our board. We have coax and probes right here that can read from different signal areas. This is the socket of the board, and as you can see, we can open it up, and inside of there is our chip. So we had some issues when we first got the socket and we were working on the board. This part of the board, which presses down the chip so it makes contact, or this part of the socket so it presses down chip and makes contact, was too long, and it was pressing the chip in too hard that it was almost breaking the chip, and we were getting inconsistent contact with the board. So we actually had to sand down this part of the socket, but now it closes nicely and it works perfectly. If I can close it, there we go. So it's all good now. So I'll run you through a little bit of the power on process. So here's our power supply. So we have two settings right now. So we have 3.3 volts and we have 1.2 volts that get connected through these cables to this part of the board right here. So I'll run you through the power on process. So we set on 3.3 volts in the first place, wait for this to go high. Once this has gone high, we can go 1.2 volts, and then this will go low. Make sure that our board's on, the Pico's running fine. Here's the Raspberry Pi Pico, which is plugged into our computer, which has all of our code on it. We have some probes right here that run to the oscilloscope, where we can run tests for different things like rise and fall times and voltages. And then we have, on one of our coax connectors, we have our waveform generator.
Hey, I'm Adam. I'm going to talk about how the actual flow process of a test works. So everything here is controlled by our code, obviously. So we're going to do a flow. It's going to run and control the Pico board, which is going to send its signals of what it needs from the chip. So it's going to enable some signals, and it's also going to talk to whatever instrument is using the input. So in this case, it's our waveform generator. It'll turn on the waveform generator, send a signal through the chip, and then we're going to compare the input and output signals. So both of the input and output signals are fed to the oscilloscope, and then we'll compare the two of them and get whatever time difference we have, depending on what test we're running. And the result is also going to be fed back into the computer and stored here on a text file that is timestamped. It'll be our output there, and then that's what's actually going to be delivered to Certus as the measurement we took.
Hi, my name's Simon. I'm going to be taking you through the process of the actual instrument scripting and go a little more in depth. So right here we have our propagation delay flow that Adam went over. If we go into this portion right here where we're taking the result, we'll pull up this file, and this is the scripting file. So we'll see transaction delay. It takes some inputs such as the input channel, output channel, maximum voltage, and the frequency of operation. And then as we come down here, you'll see our Pi Visa module being used, where we connect to the instruments and send initial resets. And then throughout this code, mostly is just set up for the waveform generator like we see here, and then also for the oscilloscope as we'll see here. As we get into the further down the script, we'll see the trigger being set up on the oscilloscope. This is important for the actual measurement being taken. And then down here, we'll actually configure the measurement to be taken. And then this is all just processing. We'll see how it's actually connected using GPIP connectors. So everything is able to be daisy chained together. So if we run a test from here where we have 3 set up, this is gonna measure rise time, fall time, and then propagation delay. We'll run it here, and then we'll watch the oscilloscope to show it happening. We'll see rise time, there is our fall time, and here's propagation delay. All of these results are logged in their corresponding files, and then also for some debug purposes, we can see them here in the terminal being outputted. So yeah, that is how the instrument is scripted. Thank you.
Hello, my name is Jake. I'm going to be explaining the Pico, what we have going on here. So this was our original code for the Pico. It would be a file, and it would define all the pins through here. And then down in the lower section, it would set all the pins on. And originally, we were going to have to call this file to upload it into the Pico, and we'll have to do that for every single test. We realized that would be a lot of files, considering for each each test we run, we got to have 8 different control signal combinations, so it was going to be a lot of files to run. So instead, we went ahead and swapped to this format. This format using subprocess will upload this code right here to our Pico. And what it does is it'll define the pins like we saw earlier, but it'll also set the value in one line. This section is just a to turn everything off, to flush it kind of, just so we don't have any like miscellaneous signals going high. And so the way Python works is it's going to read this value, this %d, and it'll go down to here and choose that file, and it'll go on from each one past that. So that's how our code works. We had a few issues with it. Originally, we had all these DFTX enable definitions in a different file. And so when we called it, we would have to do like pico.defines or pico. Whatever the value is. And it ended up taking a lot more memory in the Pico. And so we think that we couldn't write to it because there was too many characters. So it would only take like the first however many lines. We came across another issue with the Pico. We didn't define these pins every single time. So if we unplugged and replugged our board, the pins wouldn't be defined, so we couldn't run the code without defining them again. So we changed our code just to have this comma pin out section. So every time it runs, it'll define every single pin. So we shouldn't have a issue uploading anymore. We then we made a definition out of that, and then we call it in other files. For instance, right over here, we have Pico from Pico upload, import Pico upload, and Pico upload off. Pico upload off, we'll just turn everything off at the end of a test to make sure nothing's on, we're not wasting energy. This is us actually calling the function. So the DFTX enable value equals is completely optional in this code, but just for visualization and like being able to see it and map it clearly, we keep it in there. So this specific code is going to turn on the GPIO OE, the GPI eval, and the H4 just to run a test. So that is the example of our Pico code.